So the last little bit to lock up the Redfield theory is we are going to make a simplifying assumption about the nature of the fields and their correlation functions. Okay, and then what you'll see, we'll put them back into the sort of giant equation that we had second to last of the previous one, and then I'll show you the general formula for that, and then that'll be our most general possible Redfield equation. Of course, when you do a real system, especially if you're doing it by hand, it'll be a little bit smaller, a little bit more manageable. Okay, so the way we're going to do this is, remember we had all these field correlation functions. So for example, if I have EM0 En of tau, right, remember what this is. This is you multiply this field EM at time 0 by En at all these other times. Of course, it's going to look like noise, but when you average it over many, many times of doing that, you'll get something that probably has some functional form. Okay, so we're presuming, first of all, that there's no correlation between different field types. All right, so N and M are different field types. They correspond, right, to different operators in the system. So we're going to assume that those are uncorrelated. So the first thing that we do is we have this delta function, which just says if En and Em are different, the correlation is 0. Okay, and then we're going to presume that there's an average value, right? So the mean squared value of the field, right, like a variance. Okay, so there's some static property that tells you about the size of the fluctuations. So this is like the magnitude of the fluctuations. Right? And then we have a time scale for the decay of the correlation. I guess tau. I use tau. Tau over tau c. I think I'll just switch this to t. There's no need for this to be tau. All right, so what does that mean? It just means that we've chosen it to decay exponentially. Is that reasonable? Yeah, it's pretty reasonable. Many things, even if they're not truly exponential, are so close to being exponential as to be indistinguishable, experimentally or even numerically. So for the purposes of generating formulas that we can analytically investigate, meaning not rely on numerical simulation, you have to pick some form. So this is the one that is very common to pick. And then we can just use some substitution. So instead of tau c, we'll define 1 over tau c is equal to 2 pi times zeta. Is it zeta? Yeah, zeta. All right. And so that just means that we have a rate constant instead of a time constant. So it doesn't really make any difference. Just when we do putting it back into the Redfield equation, it's more convenient to work in terms of a rate constant than a time constant. All right, so I know it's harder with the lecture segments, but if you look back on the previous one, there was that giant equation with the sums and all the integrals. Right? That's what we're kind of looking at. So imagine we picked out one of the terms. So one of the terms of the integral was something like this: 0 to infinity d tau. Then we have one of these fields, EM0 En tau. And then in the integral, we had e to the 2 pi I omega tau. Okay? And what this is, of course, is related to the Fourier transform. Like normally a Fourier transform has it going from minus infinity to plus infinity. This is a time correlation function. So those are actually even functions. They look the same going this way as they do this way. So that means if you have the integral from here to here, you can just double it and get the integral from here to from there to negative infinity as well. So when you work the math out, so this is literally just math. You can do it in Mathematica if you like, or you can look it up. The delta part's not from the math. That's from our assumption here about this, right? Of course, we have the e squared, which is the magnitude of the fluctuation, right? And then the math part is just the stuff on the bottom. So 2 pi times this zeta factor, the decay constant of the fluctuation, and this complex frequency, I omega. Okay, so that's what happens when you integrate that function. It's just math. There's no physics or there's no assumptions to get to there. Okay, so what we're going to do is we're going to use this. Now we see what it's defined in terms of frequency, right? So we're going to call this J of omega. And actually, let me be more careful because it turns out that's not the right way that people define it. So J is actually, so, all right, the delta NM is not part of J of omega. And then for reasons I'm not exactly sure, but there's some sort of reason, we take the 2 pi part out. All right, so that just tells you what J is. J is like everything else, right? It's this. All right, so we have converted these time correlation functions and the integral with respect to this frequency. Now it's going to be different for all those different frequencies. If you remember all of the complicated formulas, they had all these different frequencies in there. So the omega is not going to be like omega. It's going to be the different frequencies that we had. All right, and the J has a name. It's the spectral density. So it's a spectral density function, all right? So if you had like an exponential, the Fourier transfer of an exponential, well, this is the function right here, so you can just look at it. Now it's complicated because it's complex, right? All right, so you might not be able to plot just J by itself, but it's going to look, you know, it would look something like a Lorentzian if you could plot the magnitude of it. A Lorentzian's a little bit like a Gaussian, it's more pointy and it decays like a polynomial at long time instead of an exponential. All right, so now what we can do then is we can go back to that super long equation, plug in all the J's in place of those integrals, right? So we get rid of the integrals. That's a good thing, right? We want to get rid of integrals whenever possible. So we're going to write this down now. We have that. This is going to be our super duper ultra Redfield equation. All right, and the first part that we had was this part that came from the unitary evolution of the Hamiltonian, you know, under the Hamiltonian that's time independent. Okay, and then we're going to have these, what is it, 4 terms. Let me see, make sure I understand. Oh, no, actually, it's only 3 now because of the compact notation that you can derive. I'm not doing every single step because some of them are the math steps that are, there's no physical insight from them. So some of this should look somewhere. Now we have our first J function. And if you look back to the integral, then you'll see that there was, in that term, there was a exponential, and the exponential had the energy as beta minus gamma. So we're going to put in beta minus gamma. Now remember, these are the eigenvalues of the Hamiltonian, the field-free Hamiltonian. In the units that we're using, the energies and the frequencies are the same, right? Because the Planck's constant, h bar is equal to 1. So you just be a little careful when you do your own calculations that this is really supposed to be, this is a function of frequency. So it's the frequency, it's the energy of the beta minus the energy of the gamma divided by h bar. So if you use real numbers, this will be that. All right, so we're going to plug in all of those. And then there's a really clever notation that compactifies a little bit of this. So this is the actual matrix element. And then it turns out you can write it in this way, where the dot here means to take the scalar product. And so I'll explain what that is in a minute. It just simplifies this formula quite substantially. Remember, the A's are the operators that are actually in the system. So, you know, what might they be? They might be like position, or they might be position squared. Or, you know, you have to figure out what is the functional form by which the system Hilbert space is coupled to the bath. Okay, so there we have that. And then that's the first term. I have a minus sign. And then another J. alpha primed minus beta primed, and then plus j beta minus alpha, and then another one of these clever scalar product things, which I'll define for you in a minute. All right, then the next term is plus delta alpha beta. We have our sum over gamma again. J gamma minus beta primed. So if we're careful with all of this, we closed there, and this is closing here. And all of this is multiplying or operating multiplying. This is just one term. Beta, beta prime. Right? So again, you could pick out the terms here that correspond to that gamma operator, the Redfield operator, relaxation superoperator. Just for the definition of this inner product thing, for example, you have A beta primed alpha primed dot A alpha beta would be equal to the sum on n. What is the, remember, n is the operators. There was multiple operators. There were, we listed the operators by an times the field en. Right, so what we're doing here is we're writing the sum on n, an, b primed, alpha primed, an, alpha beta. Now, why do we have only n and not the m? Right? The reason is because of this. Right? Because of the delta functions, we don't have to worry about the sort of cross term between two different system operators. We killed that off by making the fields themselves be independent, however you want to think about that. All right, so this is not obviously not very transparent. When you do the example for the problem set, it'll be much more clear what's going on. In general, there will be terms that tell us about relaxation of population. There'll be terms that tell us about relaxation of coherences, so dephasing or decoherence. And then those come from a product of two contributions, and this is general and very true and very important. They come from the matrix elements that connect the states and the spectral density. So once you have those two ingredients, you can actually numerically, obviously, or in the in a problem set we're doing it analytically. But if it's multiple dimensions, it's going to be hard to do it analytically. You can solve it numerically, right? Now it looks, because we've got it written here as a time dependence of an operator, but we know how to convert this operator to a vector. We convert it to a vector, which means we basically do the calculation in Liouville space. So we have a vector of derivatives, a matrix, which has the unitary part as well as the relaxation dissipative part, and then we have a vector of density operator elements. Okay, and then you can just plug that into any linear differential equation solver, and you can propagate the density matrix as a vector to your heart's content. Obviously, there's, you have to worry about what happens, but you can do it. And the cool thing is you can solve this, and then you can add into it, another field, right? So you can add into the part that's not the relaxation part. You can add a field, right? There's no reason you can't do that. So then you add a field, and by adding a field, like for example, you can have a laser field that comes on and then turns off. So your system might, we've seen this before, how this works, right? Your system starts in the ground state. You ask, what's the probability I'm in the excited state, right? Well, then the field is on, and then maybe if you're on resonance, it's going to go up, and it's going to hit some final value, Now, if there was no Redfield, if we just had unitary evolution with a field, it would stay like this forever. But the point is now, as the system is being excited, there will also be dissipation. And so it'll actually come back down and it'll decay. Now it'll decay on some time scale. Who knows what time scale it's set by a rate constant. That would be like if the excited state was B, for example, then you would be looking at going from a population in B, excited state, to the ground state by this matrix element. This matrix element will have a contribution if you want to get like a deep input, like if you wanted to say, I want inputs only from things that are ab initio or that I can somehow measure somewhere or postulate, then you would have a contribution from the coupling between the two states, and you would have a contribution from the fluctuation of the bath or the spectral density evaluated at the frequency difference between these two. Right? That's how it works. That's the primary theory that we have for relaxation, energy transfer, and the way we model it so far here. Just I would have to put the system in a state. Right? Obviously, if it was in the ground state, probably nothing would happen. If I put it in an excited state, then this would ensue. To do spectroscopy, I need to put a field on that actually does something. So that's something that we can do. All right, what's next? The next thing is we're going to develop, it's actually pretty quick, a stochastic theory of line shapes. This is probably one of the most useful things that you will learn because it immediately gives you a molecular picture, a chemically relevant picture about why some spectroscopic line shapes look one way and some look another way in terms of their width mostly, but also in terms of their functional form. It was traditional in the old days to measure a spectrum and then fit it to some function, and then depending on how well you could fit to that function, you would then pronounce something about the nature of the dynamics. Now we know better now. We know that no amount of fitting can do better than a multidimensional spectroscopy method, which can tell you directly what's going on as far as the dynamics. But nevertheless, it's a good place to start. So that's what we'll do next. It's called the Kubo line shape theory.